Hi everybody. In this video, we're going to talk about what it means to have an exponent of 0 or a negative exponent or a fractional exponent. But before we do that, let's talk a little bit about rules in general. So the rules we invent in math must be consistent. If we have a bunch of rules that we're learning, we need to make sure, or inventing really, we need to make sure that those rules which we invent are consistent with each other, meaning they don't contradict each other. And in this way, inventing the rules of math, which is done all the time, continues to be done to this day, is very much the same as inventing the rules of a game. So here I have an example. Maybe you've played dodgeball before. We're going to invent our own rules for, let's say, a different version of dodgeball. And here are the rules that I've come up with so far. Rule number 1, if you hit a person with an orange shirt, you get 5 points. Rule number 2, if you hit a person with a yellow shirt, you get 10 points. Okay, so far so good. If I see somebody with a yellow shirt and somebody with an orange shirt, I'm probably going to want to aim for the person with the yellow shirt because I would get more points that way. Right now we only have 2 rules. Let's see if we can invent another rule. 2 rules is not really that much, right? So let's see. How about if you hit a person with blue pants, you get 20 points. So now I have to ask myself, since I just created this new rule for the game, is this rule consistent with the 2 rules that I had before? And if you think about it for a little while, you might realize that it's not consistent because, for example, take a look at this poor kid over here who's just getting pummeled. He's wearing an orange shirt and he's wearing blue pants. Well, what happens if we hit a kid with an orange shirt and blue pants? According to rule number 1, we should get 5 points because he has an orange shirt. But according to rule number 3, which we just came up with, we should get 20 points because he's wearing blue pants. Well, which one is it? Is it 5 points or is it 20 points? We don't know. The rules that we came up with are not clear on that, okay? So that's a problem. The rules contradict each other, and so we would not be able to play the game with the rules written out this way. If we started playing it, people would get into fights. Oh, you should get 5 points. No, I deserve 20 points, and we would have to stop playing, which I suppose is good news for this kid over here. All right, but anyway, now let's move on to exponents. Now remember in the last video, we came up with some rules for what it means to have an exponent which is a natural number. So if an exponent is a natural number, the natural numbers being 1, 2, 3, 4, 5, etc., then it simply tells you how many times to multiply the base with itself. So for example, so that's a problem. The rules contradict each other, and so we would not be able to play the game with the rules written out this way. If we started playing it, people would get into fights. Oh, you should get 5 points. No, I deserve 20 points, and we would have to stop playing, which I suppose is good news for this kid over here. All right, but anyway, now let's move on to exponents. Now remember in the last video, we came up with some rules for what it means to have an exponent which is a natural number. So if an exponent is a natural number, the natural numbers being 1, 2, 3, 4, 5, etc., then it simply tells you how many times to multiply the base with itself. So for example, let's say 8 to the power of 1 is just 8. 8 to the power of 2 is 8 times 8. 8 to the power of 3 is 8 times 8 times 8, and so on. So these are perfectly well defined, but what does 8 to the power of 0 mean? what does 8 to the power of, let's say, -5 mean? What does 8 to the power of 3/7 mean? Well, as of right now, it doesn't mean anything because we haven't invented a rule for that. Okay, it's like if we go back to the dodgeball example and we ask ourselves, okay, what happens when you hit somebody with a purple shirt? Well, we haven't invented a rule for that yet, so we don't know what happens. So this is what we're going to be doing in this video. We're going to be inventing rules for what happens if we take a number and we raise it to the power of 0, or to a negative exponent, or to a fractional exponent. While we're doing that, we need to make sure that the new rules that we come up with are consistent with the rules we already learned in the last video. So for example, you might think that we should define something raised to the power of 0 as 0, but it turns out that if we do define it this way, it would be inconsistent with the rules we learned before. So even though it looks like it should be written this way, there would be problems if we defined it that way. So it's defined in a different way, and I'll show you that right now. All right, that's the first one we'll do. Anything raised to the 0th power, except 0 itself, is 1. It's not 0, it's 1. So A here just stands for any number except 0. So you see over here I wrote for A not equal to 0. That means we can choose any number we want for A except 0. So A could be 3, A could be -6, A could be 27.7. All right, A is anything except 0. The rule which we're going to invent right now, the rule which mathematicians have invented, is that if you take a number and you raise it to the power of 0, you get 1. These 3 lines over here means that we are defining it to be like this. We're not figuring out that it's like this based on the other rules. We're defining it to be this way, which means we are inventing the rule to be this way, although we did invent it this way so that it is consistent with the other rules. Let's look at some examples here. So 9.63, for example, to the power of 0 is 1. Let's look at something really messy. -8 to the 3rd over 7 to the 7th raised to the power of 0 is, again, just 1. You see how easy it is? No matter what's here, if you raise it to the power of 0, you get 1. Except if the base itself is 0. If the base is 0 and we're raising it to the power of 0, that's undefined, meaning we don't even have a rule for that. Okay, this rule applies for any number except 0. If it's 0 itself over here as the base, then there is no rule for that. It is undefined. All right, so that's the definition. Now let's try to understand why this definition was created this way. And to do that, let's look at an example. Let's take this expression, let's say 5 to the 4th power divided by 5 to the 4th power. And let's try to evaluate that, see what it's equal to. And we'll do that in a couple of different ways. One way that we could evaluate that is by looking at one of the rules which we learned in the last video, which is that when we're dividing terms with the same base, we subtract the exponents. Well, here I have the same base, 5 and 5, so I should subtract the exponents. So this exponent is 4, this exponent is also 4, so I'm doing 4 minus 4. What is 4 minus 4? 4 minus 4 is 0. So we just figured out based on this rule that 5 to the 4th divided by 5 to the 4th should be equal to 5 to the 0th power. But there's another way that we can evaluate this expression. Let me write it again. Notice that what we have here is some number. 5 to the 4th is just some number. You can work it out and see exactly what number it is. Okay, it doesn't really matter so much. 5 to the 4th is just some number, and we're dividing it by another 5 to the 4th. So we're taking some number and we're dividing it by itself. Well, any number divided by itself is 1, right? Like 7 divided by 7 is 1. 10 divided by 10 is 1. Negative 3 divided by negative 3 is 1. Any number divided by itself is 1. So that's another way that we could evaluate this expression. Now look at what we have here. We have this expression 5 to the 4th over 5 to the 4th. And we figured out that it's equal to 5 to the power of 0, but it's also equal to 1. Now, a few minutes ago, before I told you this, you might have thought that something raised to the power of 0 is equal to 0. But now hopefully you'll realize that if we defined it like this, then we would get an inconsistency. Then we would be saying that 5 to the 4th over 5 to the 4th is 0, but 5 to the 4th over 5 to the 4th is also 1. And that doesn't make sense. How can something be 0 and 1 at the same time? So the only way out of this problem is if we define something raised to the 0th power to be 1. That ensures that everything is consistent. So we can evaluate this expression by using here it is, this rule over here, or we can evaluate this expression by just saying that something divided by itself is 1, and no matter which way we choose to evaluate it, we get the same answer, so there's no problem. All right, so let's move on now to a number raised to a negative exponent. So a number raised to a negative exponent is the same as 1 over the number raised to the opposite of that exponent. And the opposite of a negative number is positive. So if we have a to the negative b, we are defining that to be 1 over a to the b. And remember, when we define something, it means that we are inventing this rule now. We didn't have this rule before, but now we're sort of adding this rule to our game. So let's go ahead and look at some examples. 5 to the negative 3rd power, according to this new rule, would be equal to 1 over 5 to the positive 3rd power, which is 1 over 125. Where did 125 come from? That's just 5 to the 3rd power. 5 times 5 times 5 is 125. Okay, next example. Negative 5 to the negative 3rd power would be equal to 1 over negative 5 to the positive 3rd power. Notice something very important here. Here, the base was negative. Here, the base is still negative. The base does not change sign. Look at the rule. Here we have a base a. Here, the base is also a. The base is not changing sign. It's the exponent that's changing sign. So this negative 3 became a positive 3. So negative 5 to the negative 3rd power is equal to 1 over negative 5 to the positive 3rd power, which is 1 over negative 125. Where did this number come from? If we do negative 5 to the 3rd power, that's negative 5 times negative 5, which would be positive 25, times another negative 5, and then a positive times a negative is negative, so we would get negative 125. All right, last example here, g to the power of negative p would be equal to 1 over g to the power of p. So since I don't know what G is or what P is, I can't simplify this any further like I simplified these over here. All right, so that's negative exponents. And now let's talk about why this rule has been defined this way, and how it's consistent with the other rules that we already have. To see that, let's take an expression. Let's do 5 to the 4th power divided by 5 to the 6th power now, and evaluate this in a couple of different ways. And what we want is that the answer is the same both ways. So we can evaluate this by going back to that same rule we used a moment ago, and which we learned in the other video, which is that if we're dividing terms with the same base, then we should subtract the exponents. So according to that rule, this would be equal to 5 raised to the power of 4 minus 6. Now 4 minus 6 is negative 2, so this would be 5 to the power of negative 2. And now a lot of people would pretend that I did not show you this yet. A lot of people would think that this should be equal to negative 25, which is not correct. It's not the way that this has been defined. But a lot of people think that it would be like that. And why do they think that? Because they're thinking, well, 5 to the 2nd power is 25, so 5 to the negative 2nd power should just be negative 25. That's the reasoning. But we're going to see that if we defined it this way, we would reach an inconsistency. So let's take this expression and evaluate it another way. 5 to the 4th power divided by 5 to the 6th power. Let's evaluate that by just writing all the 5s out. 5 to the 4th means 5 times 5 times 5 times 5. And 5 to the 6th means 5 times 5 times 5 times 5 times 5 times 5. Okay, so a whole bunch of these 5s are just going to cancel out. These cancel, cancel. And what we're left with is 1 over 5 times 5 means 5 squared, which is 5 squared is 25. Okay, so we get 1 over 25. If you're wondering where this 1 came from, well, hopefully you'll agree that 5 times 5 times 5 times 5 is the same thing as 5 times 5 times 5 times 5 times 1, because anything times 1 is just itself, right? So we can just sort of throw in another a 1 there, and we're not changing anything, so we're allowed to do that. Okay, so if you've been watching carefully, you might have noticed that there is a problem here. What's the problem? Well, we're saying that 5 to the 4th power divided by 5 to the 6th power is equal to negative 25, but we're also saying that 5 to the 4th power divided by 5 to the 6th power is equal to 1 over 25. These are not the same. So how could this expression be equal to this and also equal to this at the same time if these are not the same? Well, it can't be. So if we define 5 to the negative 2nd power to just be negative 5 to the 2nd power, then we reach an inconsistency. So the way out of that is, instead of defining it that way, to define 5 to the negative 2nd power to be the same as 1 over 5 to the 2nd power, which is just like what we had over here. If we define it that way, all right, just like this rule says, then this expression evaluates to the same thing no matter how we choose to evaluate it. No matter which rules we follow, we get the same answer in any case. So all the rules are consistent with each other then. All right, before we move on to fractional exponents, I want to go back and redo some of the problems we did in the last video. If you recall, in the last video, we did do these problems, even though at that time we did not know what a negative exponent was. We answered them this way. So 6 to the 10th power times 6 to the negative 12th power, we answered that by following this rule over here, which says if the bases are the same, we can add the exponents. So that would be equal to 6 to the 10 plus negative 12th power. 10 plus negative 12 is the same as 10 minus 12. 10 minus 12 is negative 2. So we get 6 to the negative second power. Over here, we have x to the 29th divided by x to the negative 6th. So using the division rule, we said that was the same as x to the power of 29 minus negative 6, because we need to subtract the exponents if we're dividing. 29 minus negative 6 is the same as 29 plus 6, which is 35. So that's how we evaluated that one. Here's how we evaluated this one. We used the power rule. Since we're raising a power to a power, we would multiply the exponents. So that would be y to the 7 times negative 2. And 7 times negative 2 is negative 14. So that's how we got that one. And for this one, also the power rule, we would do negative 7 times negative 2, which is positive 14. So we would get y to the positive 14th power there. Okay, so that's following the rules that we learned in the last video. And I sort of threw these negative numbers in there and just told you to kind of trust me that it would all work out. But now let's see that it does actually work out using the rule that we just learned for negative exponents. So let me put that back up on the screen. So here, 6 to the negative 12th power means 1 over 6 to the positive 12th power. So 6 to the 10th times 6 to the negative 12th would be like 6 to the 10th times 1 over 6 to the positive 12th. Now we're multiplying a fraction times this one, it would be a whole number. So just using your rules for fractions, this is the same as 6 to the 10th over 1. And then when we multiply fractions, we multiply the numerators together. So 6 to the 10th times 1 is 6 to the 10th. And we multiply the denominators together. So 1 times 6 to the 12th is 6 to the 12th. And at this point, we can follow the dividing with exponents rule, which tells us we can subtract the exponents. And so this would be equal to 6 to the 10 minus 12th power, which is the same thing that we had over here. And we know that's 6 to the power of negative 2. So we do get the same answer. So over here, or in the last video, when I told you that it was okay to use, which one are we doing here? Yeah, in the last video when I told you that it was okay to use this rule, so that if we were multiplying with the same base, then we would add the exponents. If you didn't believe that that was okay to do when we had a negative number, hopefully now you're convinced that it is okay, because we do get the same answer that we would get following our new rule, which tells us what a negative exponent is, right? So using the rule that 6 to the negative 12th is the same as 1 over 6 to the positive 12th, we do get the same answer that we got in the last video when we applied the multiplying with the same base rule and we added the exponents. Let's look at the rest of these examples. So x to the 29th divided by x to the negative 6th. X to the negative 6th is like 1 over x to the positive 6th. And now we can just use the rules for dividing fractions, which hopefully you know from elementary school are keep, change, flip. So we can keep this, change division to multiplication. I'm just going to write a dot for multiplication because if I write an x, then it might get confused with this x over here. And flip this, so that would be x to the 6th over 1. And we could also put this over 1. And then we just multiply the numerators. So x to the 29th times x to the 6th would be x to the 29 plus 6th power. That's using the rule for multiplying terms with the same base. 1 times 1 is 1. So we would get x to the 35th over 1, which is x to the 35th. Okay, same thing that we got before. So in the last video, if you were a little skeptical about using the rules from that video with negative exponents, which we hadn't even learned about at that time, hopefully this convinces you that it is okay, because we do get the same answer here that we got in the last video. Let's try this one over here. Y to the 7th power, all raised to the negative 2nd power. What would that be? That would be like 1 over y to the 7th power to the positive 2nd power. If that's a little bit confusing, then you can think about it this way. In this example over here, y to the 7th power is the base. It's just like the a that we had over here. And according to this rule, when we're raising some base to a negative exponent, then that's like 1 over that base to the positive exponent. So the base does not change. And that's exactly what we did over here. We just took this base and put it in the denominator, just like the base is now in the denominator over here in our definition. And then we changed this negative 2 to become a positive 2, just like we changed negative b to b over here. And then we can go ahead and use the power to a power rule and multiply these exponents here, and we would get 14, so that would be y to the 14th power. That follows from this rule over here. When we are raising a power to a power, then we multiply the exponents. So that's what we did over here. We did 7 times 2 is 14. And 1 over y to the 14th power is the same as y to the negative 14th power. That's just like using this rule in reverse. So if we start with the fraction, then we can sort of go the other way and turn it into an expression with the negative exponent. Okay, so we do end up getting the same answers again. And finally, for y to the negative 7th power raised to the negative 2nd power, that is like 1 over, in this case, I'm considering this whole thing is like the a over here. Okay, so this would stay the same when I put it in the denominator. It's only this exponent, which is like the negative b, which would change. And this was negative 2, so that'll change to a positive 2. But this would stay the same. So y to the negative 7th, all raised to the negative 2, would be like 1 over y to the negative 7th raised to the positive 2. And now we can go ahead and apply this rule again to change this y to the negative 7th to 1 over y to the 7th. So this is going to start looking really messy now. So we have 1 over We're going to change this to 1 over y to the 7th, and this is being raised to the 2nd power, so we need to write that exponent there. Okay, and so now let's think about what we have here. We have 1 over, what is 1 over y to the 7th power squared? That means we're taking 1 over y to the 7th power and we're multiplying it with itself. Let me do that on the side here. 1 over y to the 7th power squared means 1 over y to the 7th power times 1 over y to the 7th power. So 1 times 1 is 1, and y to the 7th power times y to the 7th power is y to the 14th power. Okay, we would, since we're multiplying these things, we would add the exponents. 7 plus 7 is 14. Okay, so this is what we should put over here now. Okay, we just figured out that this is equal to this, and here's the work that we did for that. And now we can go back to elementary school again and do keep, change, flip, because we're dividing with fractions here. So we have 1 divided by 1 over y to the 14th. Okay, 1 divided by this fraction over here. So let's keep the numerator, 1, change division to multiplication, and then flip the denominator. So 1 over y to the 14th would become y to the 14th over 1. And we can put this 1 over 1 also. Now we're multiplying two fractions, so we just multiply the numerators and multiply the denominators. 1 times y to the 14th. Anything times 1 is just itself, so that'll just be y to the 14th. 1 times 1 is 1. Anything divided by 1 is also itself, so this divided by 1 is just this. So y to the 14th power. So once again, we got the same answer using this rule that we got in the last video when we didn't even know what a negative exponent was. So hopefully that convinces you that the answers that we got in the last video are actually correct. Okay, so we've covered a lot of ground. Now we know what it means for something to have an exponent which is a natural number. So for example, 7 to the 4th power means 7 times 7 times 7 times 7. We also know what it means. We know what an exponent of 0 means. So something raised to the power of 0 is just 1. Okay, except if that number is 0, then 0 to the 0th power is undefined. Anything else to the power of 0 is 1. So we know what it means to have an exponent which is a natural number. We know what it means to have an exponent which is 0. We know what it means to have a negative exponent. A to the negative b is the same as 1 over a to the positive b. That's the way it's defined. What we need to know now is what it means for an exponent to be a fraction. So here is the way that has been defined. Let's start with a fraction where the numerator is 1. When an exponent is a fraction, 1 over c, where c is just some number which is not 0, this is defined to be the same as taking the cth root. So a to the 1 over c is defined to be the cth root of a. So let's do a couple of examples. What would 49 to the power of a half be? Well, according to this rule, that would be defined as the second root of 49. This is also called the square root. If this is a 2, then you also call that the square root of 49. Actually, you might be familiar with a square root. If you've seen a square root written before, then you might have seen it written without the 2. Because for square roots, people don't usually write the 2 in there. But you can, and just to be clear here, I'm going to write the 2 in there so we can really see how this follows from this rule right over here. But what does the square root of 49 mean? That means we're looking for the number that we can multiply with itself in order to get 49. So what number is that? What number times itself is 49? That would be 7. So the square root of 49 is 7. All right, let's do another example. What is 16 raised to the power of 1/4? Well, again, according to this definition, that would be the same as the 4th root of 16. Well, what is that? So we're looking for the number that we can multiply with itself until we get 4 of them. And when we do that, we get 16. So what number multiplied with itself 4 times like this gives us 16? Well, the answer to that would be 2, because 2 times 2 is 4, times another 2 is 8, times another 2 is 16. So 2 is the 4th root of 16. So we have this new rule, but again, anytime we come up with a new rule, we want to make sure that it's consistent with the other rules, right? So I want to just do an example to show you, to demonstrate how this rule is actually consistent with other rules that we know. Let's say I wanted to evaluate the expression 49 to the 1/2 power times 49 to the 1/2 power. Well, according to this rule, 49 to the 1/2 power is just the square root of 49. So 49 to the 1/2 times 49 to the 1/2 means the square root of 49 times the square root of 49. Okay, if this is a 2 over here, then we don't have to write the 2 actually. So this just means the square root. That's what I have written over here. The square root of 49 times the square root of 49, what would that be? Well, the square root of 49 is 7, so we have 7 times 7, which is 49. Okay, so that's what we get if we evaluate this expression with this rule in mind. But we have this other rule. I'm not going to scroll up to it. I'm just going to write it down here. Remember this rule where we said a to the b times a to the c is equal to a to the b plus c. What if I wanted to use this rule to evaluate this expression? So I'll write the expression again. 49 to the 1/2 power times 49 to the 1/2 power equals, according to this rule, since the bases are the same, I can add the exponents. So that would be 49 to the power of 1/2 plus 1/2. 1/2 plus 1/2 is 1. So this would be 49 to the power of 1. 49 to the power of 1 is just 49. So you can see, yes, I do get the same answer by evaluating this expression using this rule that I get when I evaluate the same expression using this other rule. So that's a demonstration that these two rules are consistent with each other. So that's what we want. We want the rules that we come up with, the rules that we invent, to be consistent. We don't want them to contradict each other. It would be really bad if I used this rule and I got one answer, and then I used this rule and I got a different answer. That would be really bad. But we can see that we do get the same answer here, so that's good. So now we know what it means to have an exponent that is a fraction with a numerator of 1. But what about when the numerator is not 1? Well, here's that definition. When an exponent is a fraction, let's call it b over c. So now the numerator is just some number b, which might be 1, it might be some other number. And c is the denominator, which is not 0. We don't want the denominator to be 0 because dividing by 0 is undefined. All right, so anyway, when an exponent is a fraction b over c, this is defined to be the same as taking the cth root and then raising to the bth power. So for example, if I have a to the b over c, that's defined as taking the cth root of a and then taking this whole thing and raising it to the bth power, so multiplying it with it out b times. All right, this, by the way, is the same as taking the base, raising it to the bth power, and then taking the cth root. So actually the order does not matter, and we're going to show that in a little while. But first, let's give an example. So let's say I wanted to evaluate 8 to the power of 2/3. So what does that mean according to this definition? In this case, my a is 8, so that goes under the radical here. I'm taking the cth root of a, so in this case, c is 3, so I'm taking the third root of my a, which is 8. So I'm taking the third root of 8, and then I'm taking this whole thing and raising it to the bth power. So what was my numerator over here? 2. So I'm taking this whole thing and raising it to the power of 2. All right, we can simplify that. What is the third root of 8? What number multiplied with itself 3 times, so the number times itself and then times itself again, gives us 8? That actually would be 2. 2 times 2 is 4, times another 2 is 8. So the third root of 8 is 2. So we're taking 2 and then raising that to the second power. These, by the way, are not always the same. That just happened as a coincidence in this example. What is 2 to the second power? That means 2 times itself. So 2 times 2, which is 4. So 8 to the power of 2/3 is 4. All right. Now, why is this a to the b over c defined this way? Why was the rule invented this way? Well, it's actually not too hard to see that this is consistent with the power rule, which we learned earlier. So what if, for example, I wanted to evaluate 8 to the power of 1/3, all raised to the second power? Okay, so we can evaluate this in a couple of different ways, and then if we see that no matter which way we evaluate it, we get the same result, then we'll have shown that the rules are consistent. So we can evaluate this by using the power to a power rule. So we can say that this is equal to 8 to the 1/3 times 2 power. Okay, 1/3 times 2. Now we're just going back to elementary school, and we're multiplying a fraction by a whole number. We can put the whole number over 1, and then multiply the numerators and multiply the denominators. So 1 times 2 is 2. 3 times 1 is 3. So if we use this rule, then we would say that 8 to the third to the second is equal to 8 to the 2/3. All right, what if we use this rule down here? I'm going to start with the same expression, 8 to the 1/3, all raised to the second power. Using this rule, I can see that 8 to the 1/3 power is the same as the third root of 8. And then I'm taking that and raising it to the second power. So I'll put this in parentheses, raise that to the second power. Okay, so using this rule, I get this. So I took the same exact expression, and evaluating it one way, I got 8 to the power of 2/3. Evaluating it another way, I got the third root of 8 squared. So going back here now, a to the b over c is equal to the cth root of a to the bth power. 8 to the 2/3 is equal to the third root of 8, all raised to the second power. That's following this rule, which actually we did a couple of minutes ago over here. All right, and so you can see that this is exactly the same as this. And in fact, that's why this rule was invented the way it was. It was invented this way so that we would get the same answer here and here, so that all the rules are consistent, and no matter which rules we use to evaluate some expression, it all ends up giving us the same answer. Okay, the last thing I want to do here is to show you that this really is the same as this. In other words, if I have some number, if I take the cth root of that number and then raise all that to the bth power, that's the same thing as taking that number, raising it to the bth power, and then taking the cth root. So over here, over here we did that this way, where we had 8, we took the third root of 8 and then raised that to the second power. The third root of 8 is 2. 2 to the second power is 4. Let's do it the other way. This time, we're going to start with 8, raise it to the second power first, and then once we do that, we will take the third root. So let's see that we actually do get the same answer. 8 to the second power means 8 times 8, which is 64. So here we have the third root of 64. And now what is the third root of 64? In other words, what number multiplied with itself so that we have 3 in a row gives us 64? That number is 4. 4 times 4 is 16, and then 16 times another 4 would be 64. So you can see that this and this do evaluate to the same thing. And here's a little proof of that down here, so that it's not just for the numbers 8, 3, and 2, but for any numbers. Now this proof might be a little bit tricky, so if you just want to stop the video here and call it a day, that's fine, no shame in that. If you feel up for a challenge, then you can try following along with this proof here. So what I've done is I've taken, let's see, I took this expression, I wrote it over here, and then I raised it to the power of c. And I did the same thing with this one. I took this expression, I wrote it over here, and then I raised it to the power of c also. All right, now stick with me here. We have something under the radical, and we're taking the cth root of that and then raising all that to the power of c. So what would the result of doing all of that be? I'm just going to shade this in, okay? Because a to the b looks kind of messy. I'm just gonna forget about what's behind that dot. Let's just say that there's something underneath this radical. What would happen if we take the cth root of that and then raise it to the power of c? What would we get? Well, as an example, let me go back to 16 to the power of 1/4, which we did earlier. And you know what? I'll write it this way. Let me take the 4th root of 16 and then raise that to the power of 4. What would I get? Well, we said earlier the 4th root of 16 was 2. So this is equal to 2. And then I'm taking that and raising it to the 4th power, which means that I'm doing 2 times 2 times 2 times 2, which is 16. So I started with 16, I took the 4th root and then raised the whole thing to the 4th power, I got 16 back. Well, that kind of makes sense because the 4th root of 16 just means the number that we need to multiply with itself 4 times to get 16 back. And we are doing exactly that because we're raising that to the 4th power, which means we are multiplying it with itself 4 times. So it makes sense that we would get 16 in the end. Well, the same idea holds over here. If we have something behind that dot, forget about what it is for now. If we take that something and take the cth root of that, and then raise it to the cth power, we should get whatever that something is back in the end. Okay, now let's just remind ourselves what that something was. It was a to the b. Okay, so in the end, we would get a to the b over here. All right, now for the next one, which started here and then we raised it to the cth power, we have the cth root of a raised to the b, and then all of that raised again to the power of c. Well, we can use the power to a power rule here and say that if we take something and raise it to the bth power, then raise it to the cth power, that's the same thing as taking that something and raising it to the b times cth power. Remember, if we're raising a power to a power, then we multiply the exponents, okay? But b times c is the same as c times b, right? Commutative property. Right, but that's the same thing as taking this and then raising it to the cth power and then raising it to the bth power. Actually, we could have skipped over all of this and just gone straight from here to here. If you just sort of remember in your head what this means, it means we're taking this, we're taking b of them, and then we have c groups of b of these. That would be the same thing as b groups of c of these. So, for example, if this was a 3 and this was a 4, this was a 4, that should be the same as if this was a 4 and this was a 3, because if I have 3 of these and then I have 4 groups and each group has 3 of these, that's the same thing as having 3 groups where each group has 4 of these inside of it. So we sort of could have skipped these steps over here and just gone straight from here to here. But anyway, if you like just manipulating symbols, then this might be fun for you. So anyway, what is this over here? Now we have something over here which looks similar to what we had back here. Whoops, where did this go? That was a to the b, right? Okay, so we have a, we're taking the cth root of a, and then we're taking all this and raising it to the power of c. Well, that would just give us a back, right? Just like when we started with a to the b and we took the cth root and then took the power of c, we got a to the b back. If we start with just a and we do all that, then we'll just get a back. Okay, so this whole thing is just equal to a, but then we're taking that and we're raising it to the power of b. So what we have all together here is we have a to the power of b, which is exactly the same answer that we got back here. Now, what does that tell us? We started with something, and we raised it to the power of c, and we got this. Then over here, we started with something again, and we raised it to the power of c, and we got the same thing as what we got before. The only way for that to have happened is if these things were the same to begin with. The only way I can have a number and raise it to some power and get the same answer as another number raised to the same power is if really the two numbers that I started with were the same to begin with. So the fact that I got the same answer here tells me really that this is exactly the same as this, okay? If that's a little hard to understand, let me do a little analogy. Let's say that I'm going to just draw a star here. This star is like a variable. It just stands for some number or some unknown. Okay, let's say star plus 5 is equal to, I don't know, whatever, 14. And let's say also that smiley face plus 5 is equal to 14. Well, if some number plus 5 is equal to 14, and then some other number, which plus 5 is also equal to 14, then really these two numbers must be the same as each other, right? So that's like the reasoning that we have here. If this thing to the cth power is this, and this thing to the cth power is exactly the same, then really these things must be the same also. Okay? And notice that we didn't even have to know what the A and the B and the C were in order to prove that this was the same as this. So that means that these expressions are the same, just like I claimed before, no matter what numbers we plug in for A, B, and C. Okay, so I'm going to end the video there. Congratulations to you if you at least attempted to watch all the way to the end, and have a great day.